Hey, this is Presh Talwalkar. In this video, I want to share a really fun problem. Let n be equal to the square root of 5 plus the square root of 6 plus the square root of 7 and so on until the square root of 13. The challenge is to prove that n is between 26 and 27 and you are not allowed to use a calculator. How can we estimate the sum of square roots without directly calculating them? I saw this problem on the YouTube channel Prime Newtons, and he said it was suggested to him by a reader who said it was part of the Romanian mathematical Olympiad. From what I gather in the comments section, challenging puzzles like this were given to talented 13-year-old students, or students in the 8th grade. Not every student was expected to solve this problem, but a few talented students were able to figure out the answer to puzzles like this. But this is a challenging problem for students of all ages, and someone like me, I was still puzzled on how to solve this. But that's okay, it's a very fun problem, so in this video I'm going to illustrate 4 different methods on solving this question. Let's get started with method 1, which is to complete the square. So we need to calculate the sum of these square roots. In these problems, I like to take the very first step of writing out every single term in some cases. This helps me identify a pattern. So in this case, we have a sum of 9 different terms. The term right in the middle is square root of 9, and 9 is a perfect square, so we can evaluate this, that the square root of 9 is equal to 3. We now have 4 terms to the left and 4 terms to the right, so why don't we try a classic math strategy of pairing up terms. So let's pair the first and last terms and just continue making pairs. Now, why would we pair these terms? Let's sum the radicands. We have 5 plus 13 is 6 plus 12 is 7 plus 11 is 8 plus 10 is equal to 18. So we might think that the sum of each of these pairs is approximately the same value. So if we say that the square root of 5 plus the square root of 13 is approximately some value p, we might think that the other pairs have the same value p. So now let's take a look at our goal. We need to show that n is between 26 and 27. Now, if our analysis is true so far, then n would approximately be equal to p plus p plus p plus p plus 3. So this is exactly 4p plus 3. So we need to show that 4p plus 3 is between 26 and 27. Subtract 3 from this inequality, and then divide this inequality by 4. So we would need to show that the value p is greater than 5.75 and less than 6. So let's attempt to prove this inequality for each of the pairs. We have 4 pairs that we need to analyze, so let's work on each in turn. Let's get started with the first pair, the square root of 5 plus the square root of 13. Let's think about estimating this value by analyzing it geometrically. Imagine we have a square with an area that's equal to 5. The side length of this square will be equal to the square root of the area, which is equal to the square root of 5. Now imagine we have another square, but this time the square has an area that's equal to 13. What's the side length of this square? It will be equal to the square root of 13. So in order to estimate the value of the square root of 5 plus the square root of 13, we are essentially estimating these 2 lengths. But how can we do that? Well, let us use a strategy to complete the square. So what we will do is make these squares diagonal to each other, and now let us construct rectangles to complete a square. So we will have one rectangle over here. Now, what is the area of this rectangle? We know that one side length is the square root of 13, the other side length is the square root of 5, so its area will be equal to the square root of 13 times 5, which is equal to the square root of 65. We have another rectangle here with exactly the same dimensions, and its area will be the same. So we can now ask, what is the total area of this square that we have constructed? The area of this large square will be the sum of the areas inside of it. So it will be equal to the square root of 65 plus 13 plus 5 plus the square root of 65, which simplifies to be 18 plus 2 root 65. we now can calculate the length of the square by taking the square root of the area. So the side length will be the square root of this value, and notice this is exactly equal to the square root of 5 plus the square root of 13. So if we can just estimate this value, we will have an estimate on the square root of 5 plus the square root of 13. So how can we estimate this value? Let's first establish an upper bound. This number is certainly less than the square root of 18 plus 2 times the square root of 81 because 81 is larger than 65. We have picked this value because 81 is a perfect square. The square root of 81 is equal to 9. Then 18 plus 2 times 9 is equal to 36. And the square root of 36 is equal to 6. Therefore, we know the square root of 5 plus the square root of 13 is less than 6. We've established an upper bound. Now let's proceed to establish a lower bound. We know this square root is larger than the square root of 18 plus 2 times the square root of 64 because 64 is less than 65. The square root of 64 is equal to 8. Then 18 plus 2 times 8 is equal to 34. At this point, we need to remember our goal is to establish a lower bound of 5.75. So let's take a look at the square of 5.75. We can rewrite 5.75 as 6 minus 0.25. We can then expand the binomial, and then we will simplify each term. 6 squared is 36, 2 times 6 times 0.25 is 3, and then the square of 0.25 is 0.0625. This simplifies to be 33.0625, and that is less than 34. So if 5.75 squared is less than 34, taking square roots on this inequality will show that 5.75 is less than the square root of 34. In other words, the square root of 34 is greater than 5.75, which means the square root of 5 plus the square root of 13 is greater than 5.75. And we have precisely established the inequality that we wish to prove. We now need to show this inequality holds for each of the remaining pairs. So we proceed to the next pair, which will be the square root of 6 plus the square root of 12. So we go ahead and we complete the square with these areas of 6 and 12. Now we end up with 4 areas. We have 6 plus 12, which is 18, and we have 2 times the square root of 72. So to estimate this side length, we take the square root of the sum of these areas, and it will be equal to the square root of 18 plus 2 times root 72. And notice this is very similar to the square root of 5 plus the square root of 13 because we have 18 plus 2 times some square root. We proceed just like before. We can use exactly the same upper bound where we have the square root of 81, and we just proceed, and this is going to simplify to an upper bound of 6. So we know that 6 works in this case too. For the lower bound, we proceed the same way. We know that this is greater than the square root of 18 plus 2 root 64, and as we have shown in the other case, this is going to be greater than 5.75. So we've established this inequality. We can then tackle the third pair in exactly the same way. So that's the beauty of this pairing method, is that once we've figured out the inequality for one of the pairs, it's just going to magically work out for all the others. We know the side length of this square will be equal to the square root of the sum of these areas, which is 7 plus 11, which is 18, plus 2 root 77. We have exactly the same upper bound as before, which simplifies to be 6. And then for the lower bound, we use exactly the same lower bound because this is an even larger number. So we know that the lower bound is also true. We finally just show this is true for the very last pair of the square root of 8 plus the square root of 10. We go ahead and complete the square. We are going to have 8 plus 10, which is 18, plus 2 times the square root of 80. So the side length will be the square root of all that. We have exactly the same upper bound, which simplifies to be 6. And we will have exactly the same lower bound, and this will simplify to be 5.75. So now let's put it all together. We have this sum. Now we can pair up these terms. Now we know that we have 4 pairs. So we have the first, second, third, and fourth pair, and then the square root of 9 is equal to 3. We have shown that each of these pairs is strictly between 5.75 and 6. So we know that n is greater than 4 times 5.75 plus 3, which works out to be 26, and n is less than 4 times 6 plus 3, which is equal to 27. And therefore, n is exactly between 26 and 27, and this completes the first method's proof. I believe this was the intended solution because this would be accessible to 13-year-old students. However, it's not the shortest solution. With a little bit of advanced mathematics, we can get more succinct proofs. So in the rest of the video, I'm going to present 3 proofs that depend on a little bit more advanced mathematics. Method 2, a simple inequality. This comes courtesy of a comment on the prime Newtons video by @DDIMIN. So the inequality is that the square root of a plus the square root of b is greater than the square root of a minus x plus the square root of b plus x. And this is for b greater than or equal to a, greater than or equal to x, greater than 0. To understand this inequality, let us take a look at the graph of the square root of x. So we have the graph of the square root of x, and this is going to be a concave function. So imagine we have a value a, and then we have the square root of a, we have a value b, and a value the square root of b. As we increase the values of x, we're going to kind of get a flatter graph. So the increase in the graph is going to be less and less over time. That's the idea of this inequality. So if we connect a line between the square root of a and the square root of b, notice that this line is below the graph. This is what it means to be a concave function. Now imagine from a we go x units to the left. The function value is going to drop by quite a bit to the square root of a minus x. If we go the same distance to the right of b, so we have b plus x, the function is not going to increase as much. So in order to show this inequality visually, let's take a look at the midpoint. So here the midpoint is 1/2 a plus b. So if we draw a vertical line, we can see we have one midpoint, which is going to be less than the other. So the 1/2 of the square root of a plus b is going to be larger than 1/2 of the square root of a minus x plus the square root of b plus x. So this is what we can see from the graph. All we need to do is multiply both sides of the equation by 2, and we get exactly the inequality we want. Now, this is not a formal proof. I'm going to show this in just a minute, so don't get impatient. I will actually prove it formally algebraically, but this is a visual understanding of this inequality. But with this inequality, we can actually solve the problem very quickly. So let's see how we can do this. So let's take a pair, the square root of 5 plus the square root of 8. What will be our value of x? Let's take x is equal to 1. So this sum is greater than the square root of 5 minus 1 plus the square root of 8 plus 1. Conveniently, we pick perfect squares, the square root of 4 plus the square root of 9, and that will simplify to be 2 plus 3, which equals 5. What about the square root of 6 plus the square root of 7? If we take x is equal to 2, we end up with exactly the same lower bound, that this is equal to 5. Now let's take the square root of 12 plus the square root of 13. We can take x is equal to 3, and now we have the square root of 9 plus the square root of 16, which is equal to 7. So now we have n is equal to the sum of 3 different pairs plus the square root of 9 plus the square root of 10 plus the square root of 11. The square root of 9 is exactly equal to 3. The square root of 10 will be larger than 3, as will the square root of 11. So we have n is greater than 5 plus 5 plus 7 plus 3 plus 3 plus 3, which is exactly equal to 26, and therefore n is greater than 26. We solved it like magic. Now what about the other inequality of the upper bound to 27? We can again use this inequality. So let's take the square root of 5 plus the square root of 13. We need this to be equal to the square root of 9 minus 4 plus the square root of 9 plus 4. So we have a is equal to 9, b is equal to 9, x is equal to 4. So by the inequality at the top, this is less than the square root of 9 plus 9, and the square root of 9 plus 9 is of course equal to 6. We can use this on the next pair, the square root of 6 plus the square root of 12. In this case, we take a and b to be equal to 9, and x is equal to 3, and once again we show that we have an upper bound of 6. We proceed with the next pair in exactly the same way with x is equal to 2, and finally we have one more pair where x is equal to 1, and we have an upper bound of 6. So we take 4 different pairs plus the square root of 9, and we have n is less than 6 plus 6 plus 6 plus 6 plus 3, which is equal to 27, and therefore we have established n is less than 27. Therefore, n is between 26 and 27, and we have completed the proof like magic. So before I proceed to the next method, I just want to justify this inequality. I've shown it graphically, but I now want to demonstrate an algebraic proof just so that you know it is completely true. So we will proceed by comparing the size of these terms. We have the square root of a plus the square root of b, which will definitely be non-negative, and we have the sum of square roots on the other quantity, which will also be non-negative. So if we take the square of each of these terms, it will not change the direction of the inequality. So let us take the square of each of these terms. We can then subtract a plus b from each of these terms, and that will not change the direction of the inequality. We now are comparing 2 times the square root of something. We can of course eliminate the 2, and then we have the square root of one term and the square root of another term, so we can just square both sides. That will not change the inequality because both of these are non-negative terms. So we need to compare ab and a minus x times b minus x. So let's go ahead and expand this binomial. We now have ab on both sides. We can just cancel this without changing the direction of the inequality. So we have 0 on the left-hand side, and let us now just factor the right-hand side. We have x times the quantity a minus b minus x squared. We now need to judge this quantity compared to 0. So now we remember the restriction that 0 is less than x, is less than or equal to a, is less than or equal to b. So x is strictly going to be a positive term. We're multiplying it by a minus b. A is less than or equal to b, so a minus b is definitely going to be non-positive. So we take a positive quantity times 0 or negative, so that's going to be 0 or negative. So the whole left-hand side is less than or equal to 0. Now x is a positive term, x squared is going to be positive, and we're subtracting x squared. So we're going to get more negative here. So this entire quantity is going to be less than 0. So we know this entire quantity is less than 0, and we haven't changed the direction of the inequality, so we could just bring it back up, and this proves exactly that the square root of a plus the square root of b is greater than the square root of a minus x plus the square root of b plus x. Let us now proceed to the next proof. Method 3, trapezoid areas. I credit the solution to another comment on the prime newtons video. This is by @lemlog. So we again start by taking a look at the graph of the square root of x. Now if we have a value a and the function value, we have b and the function value, let's connect these endpoints to make a line segment. Now if we take a look at the midpoint of this line is going to be less than the function value. So we have 1/2 the square root of a plus the square root of b is less than the square root of 1/2 a plus b. This is because the square root of x is a strictly concave graph. Formally, this is an example of Jensen's inequality for strictly concave functions, and it can even be generalized to more inputs and to other weights. But in this case, I'm just going to take a look at the midpoints because that's all we need to solve this problem. So now we have this inequality, and all we need to do is multiply both sides of the inequality by 2. So we have the square root of a plus the square root of b is less than 2 times the square root of the average of a and b. So how can this inequality help us solve the problem? We're first going to use it to establish an upper bound. So we use it on the square root of 5 plus the square root of 13. This will be less than 2 times the square root of their average value. Their average is exactly equal to 9. The square root of 9 is 3, and 2 times 3 is equal to 6. Exactly the same argument is going to work for these other pairs, and we're going to get that each of them is going to be less than 6. So the upper bound is fairly easy to establish. We have 4 pairs plus the square root of 9. Each of the pairs is going to be less than 6. So 6 plus 6 plus 6 plus 6 plus 3 is going to show that n is less than 27. The hard part is showing the lower bound. So the lower bound, we'll take a look at this graph, and now we're going to plot out all of the values going from 5 to 13. And now we are going to use a geometrical argument of areas. So let's construct a trapezoid between 5 and 6 and the function values of 5 and 6. What is the area of this trapezoid? Now, 6 minus 5 is equal to 1, so we have a height of 1, and the average of the bases is the square root of 5 plus the square root of 6 times 1/2. So the area of this trapezoid is 1 times 1/2 times the quantity, the square root of 5 plus the square root of 6. So now let's take a look at the area of the next trapezoid. By similar logic, this will be equal to 1/2 times the square root of 6 plus the square root of 7. And we can continue this and just add up all of these areas until the very last area. So we have 1/2 times the square root of 12 plus the square root of 13. Now let's construct another trapezoid going from the very first value to the very last value. So what is the area of this trapezoid? So the area of this trapezoid is going to be less than the sum of the areas of all those trapezoids. So the average of the bases is 1/2 times the square root of 5 plus the square root of 13. And we know the height is equal to 13 minus 5. So the area of this trapezoid is going to be less than the areas of all of those other trapezoids. So how does that help us solve the problem? Well, let us simplify the sum on the left-hand side. If we simplify the sum on the left-hand side, we get 1/2 times the square root of 5 plus the square root of 6 plus the square root of 7 and so on to the square root of 12 plus 1/2 times the square root of 13. All of the numbers in the middle will have 2 halves that combine to be a whole, but the endpoints will just be 1/2 of the value. The right-hand side, 13 minus 5 is equal to 8, times 1/2 is equal to 4. So this is the lower bound, 4 times the square root of 5 plus the square root of 13. In order to get to n, we need to add back in 1/2 times the square root of 5 plus 1/2 times the square root of 13 to both sides of the equation. Then the left-hand side simplifies to exactly be equal to n, and the right-hand side is equal to 4.5 times the square root of 5 plus the square root of 13. So all that remains is to get an estimate of this value. Now we need this value to be 26 or larger. 26 divided by 4.5 is about 5.8. So we're looking for a goal of 5.8. We use our geometric method, and from the first proof, we know that the sum of these square roots is greater than 34. So let us take a look at the square of 5.8. 5.8 is equal to 6 minus 0.2. We expand the binomial, and we get a value of 33.64. Taking the square root of both sides, we can then conclude that the square root of 34 is greater than 5.8. So we just substitute this back in. We see that n is going to be greater than 4.5 times 5.8, and that's equal to 26.1, and therefore n is greater than 26, and we have completed the proof. Let us now proceed to method 4, means. There's a famous inequality of means. Suppose that x1, x2, and so on to xn are positive real numbers. Then we have the following inequality that's true for the means. 0 will be less than the harmonic mean, which is less than or equal to the geometric mean, which is less than or equal to the arithmetic mean, which is less than or equal to the quadratic mean. There's a very nice way to visualize this in the case where n is equal to 2, and we'll take the variables as a and b. So we take a and b to span the diameter of a semicircle. The radius of this semicircle is exactly equal to the arithmetic mean, and that's going to be less than this hypotenuse, which is the quadratic mean. Then we have the geometric mean is a semichord where a and b meet, and a semichord is always going to be less than or equal to the radius, which is going to be the arithmetic mean. Finally, if we create this right triangle and we have an altitude on the hypotenuse, then the harmonic mean is going to be the leg, and that's going to be less than or equal to the geometric mean here, which is going to be the hypotenuse of this triangle. Finally, the means are equal to each other, or equality holds, if and only if all the real numbers x1 to xn are equal to each other. Using this inequality, let's tackle the problem. Let's start by taking the average of the 9 terms of n. So we want 1/9 of the 9 terms, the square root of 5 plus the square root of 6, going to the square root of 13. By the QM/AM inequality, all these terms are not equal to each other, so this will be less than the square root of 5 plus 6 plus so on going to 13, divided by 9. The sum of all these terms is equal to 81. 81 divided by 9 is equal to 9, and the square root of 9 is equal to 3. Multiply both sides of this inequality by 3, and we have n is less than 9 times 3, which equals 27. So like magic, we've established the upper bound. The lower bound will require a little bit more work, but we will use the AM/GM inequality. So in the case where n is equal to 2, the square root of AB is less than a plus b, the quantity, over 2. Multiply both sides by 2, and let me just flip this inequality. So we have a plus b is greater than 2 times root ab. So we will go ahead and just choose some convenient pairs. Let's start out with the square root of 7 plus the square root of 12. This is greater than 2 times the square root of a times b. Now a is the square root of 7 and b is the square root of 12, so their product will be the square root of 84. This is going to be greater than 2 times the square root of the square root of 81, but the fourth root of 81 is exactly equal to 3, so 2 times 3 will be equal to 6. We can do the same analysis on the square root of 8 plus the square root of 11. We then end up with the same procedure, and we end that we have a lower bound of 6. Now what about the square root of 5 plus the square root of 13? This is greater than 2 times the square root of the square root of 65. Well, 65 is going to be close to 64. The square root of 64 is equal to 8. The square root of 8 is equal to 2 times the square root of 2. So 2 times 2 times the square root of 2 is equal to 4 root 2. Root 2 we know is larger than 1.4. 4 times 1.4 is equal to 5.6. Now what about the square root of 6 plus the square root of 10? This will be greater than 2 times the square root of the square root of 60. And this is greater than 2 times the square root of the square root of 54. Now previously, the last term is 5.6, so it would be nice to pair it with 5.4. 5.4 divided by 2 is equal to 2.7, so it would be nice if we have 2 times 2.7. So let's take a look at the fourth power of 2.7. This will be equal to the square of 7.29, and 7.29 is less than 7.3. It's easy to square 73, so this works out to be 53.29. This means that the fourth root of 54 will be larger than 2.7. So this is greater than 2 times 2.7, which equals 5.4. So we can now establish a lower bound. We take n and we will pair it as we have done. And now we can substitute in the lower bounds of 5.4, 5.6, 6, 6, and of course the square root of 9 is equal to 3. So this works out that n is greater than 26, and we have completed the proof. What an amazing problem! Thanks for making us one of the best communities on YouTube. See you next episode of Mind Your Decisions, where we solve the world's problems, one video at a time.